Alright guys, welcome back to Math with Mr. Miller. I'm going to be going through some stuff about tree diagrams today as we get into probability and statistics a little bit more. On this first example, when building a tree diagram, it can be really helpful to see multiple events that occur back to back and find the probability of getting, let's say, like multiple heads or multiple tails out of so many coin flips. So it's really helpful for those independent and even dependent events that occur back to back with one another. On this first one, given a biased coin lands on heads 65% of the time, find the probability you get exactly 2 heads out of the 3 coin flips. If I start to build my tree diagram, typically we build them left to right. They can be built up and down, really up to your preference. Given the space I have here, I'm going to go ahead and build it left to right. I'm going to just start off. I have 2 potential outcomes for a coin flip. I can get either heads or tails. And we know that in this case, we're going to get heads 65% of the time, or 0.65. And that means we're going to get tails the other 35% of the time, 0.35. Then when we go and flip the coin again, it's completely independent of the first coin flip. So I'm going to get heads, tails. And I'm also going to get heads, tails. So 0.65, 0.35, 0.65, and 0.35 again, okay? Those probabilities there won't change because the coin flips are entirely independent of one another. What you get the first time doesn't change what you might get on the second coin flip. And then this says out of 3 coin flips. So I'm going to go ahead and do this one more time. So heads, tails, heads, tails, heads, tails, heads, tails, and then all my heads are going to get 0.65 as their probability, and all the tails will get 0.35 as their probability. I'm kind of squeezing that all in there. Okay. And then what we can do now, if I want probability exactly 2 heads out of 3 coin flips, well, I have a couple of different ways I can get that. I could get that by getting heads, heads, and then tails, which would be, heads, heads, tails, and I multiply the probabilities as I go down my tree, as I go down the branches of that tree. So I'm going to take that 0.65 for the first heads times the 0.65 for the second heads times the 0.35 for the third heads, because these are all independent events. So really the formula I'm technically using here is probability of A times probability of B equals their intersection. I'm just using that with 3 events rather than only 2. Okay, so probability of the first event was 0.65, probability of the second event was 0.65, probability of that third event was 0.35. Multiplying them all together, I get, rounded to 3 significant figures, approximately 0.148. Now remember, when we go and do kind of our full calculation, I should really be using the unrounded values for all of this. And that unrounded value in this case was 0.147875. I just don't want to write out that whole thing there. Okay? That's not the only way, though, I can get exactly 2 heads in 3 coin flips. I could also have gotten heads, tails, heads, okay, which is a different pathway through the tree, right? So I'm going to highlight it in blue this time. Still going down the same path for the first one, heads. But this time I go tails and then back to heads. Well, that's going to give me 0.65 times 0.35 times 0.65 this time, right? And that's happening, that probability ends up being the same, 0.148. That's because these are independent events. The probabilities through the tree don't change. If they were dependent events like what we might see on the next one, then things would look a little bit different. I would have different multiplications here. Okay. And our last one, I could also start with tails and then get 2 heads right after that. And so in my tree, I would start with tails, 0.35, and then 2 heads after, heads, heads, times 0.65, times 0.65, which also gives me approximately 0.148. Okay. And those are the only different ways I can get 2 heads and 1 tails in my coin flips. What I do at the end here, though, the probability I just get 2 heads, because it doesn't matter where those heads came up, I need to add all of my probabilities here. So 0.148 plus 0.148 plus 0.148, being careful, I'm actually adding together the unrounded version. I end up with approximately 0.444 as my probability. When I add the unrounded versions, I get 0.443625, which then rounds to 3 significant figures, 0.444. Okay. I'm going to start by reading out this one because I don't have quite a lot of room. I'm going to have to zoom in, so it's going to cut some of the problem off. But given a drawer with 6 white socks, 4 gray socks, 5 black socks, reaching in and pulling 1 sock out at a time, find the probability I get 2 socks of the same color. So I'm going to take 2 socks out of this drawer. What I'm going to do, and the key thing here, is I'm not going to replace the sock, not replacing the first sock. Okay, I'm going to zoom in a little bit so that I have a bit more room down here. So when I go to make my tree diagram, I'm going to start off pulling the first sock out of the drawer. Okay, so first sock out of the drawer. I have the chance of getting a white sock, a gray sock, or a black sock. Okay. In total, I have 15 socks in this drawer, 6 that are white, 4 that are gray, 5 that are black. So when I add all that up together, I get 15 socks. And of those 15, 16 of them are white. Or sorry, 6 of them are white. Out of the gray socks, there's only 4. So 4 out of 15. And out of the black socks, there are only 5. So 5 out of 15. Okay. When I go to take that second sock out, it's going to depend on what I took out the first time, because if I took a white sock out, there's going to be less white socks in the drawer than there are gray and black. If I took a gray sock out, well, then now there's only 3 gray socks left in the drawer rather than the 4 that originally were there. Okay, so whatever I did the first time changes the probabilities of what I get the second time. So if I drew a white sock out first, okay, I have a chance now. If I took 1 white sock out, that means there's only 5 socks that are white left in the drawer out of now only 14 socks. If I take a white sock out, that doesn't change how many gray socks are left in the drawer, so that's still going to be 4 gray socks, but there's only 14 socks left because I took a white one out. And then for the black socks, same thing. There's only 5 left there's still 5 left in the drawer because I didn't take one out, but there's only 14 socks left. I do the same thing if I take a gray sock out. Oh, whoops. Black, gray. Oh, my bad. White sock, gray, black sock, okay? If I take a gray sock out, well, that means there's still 6 white socks in the drawer out of 14 socks left. If I take a gray sock out, that means there's only 3 left in the drawer out of 14. And if I took a gray sock out, that leaves me still with 5 black socks in the drawer out of 14 socks left. And I do the same thing. Okay. I'm going to zoom in just a smidge more down here, finishing up my tree diagram. Okay. White, gray, and black. If I take a black sock out of the drawer, that means there's still 6 white socks left out of 14. If I take a black sock out, there's still 4 gray out of 14. And if I take a black sock out, that means there's only 4 black socks left out of 14 socks. Okay? So there's my tree diagram for pulling the 2 socks out of the drawer. Now what I need to do is decide, okay, find the probability you get 2 socks of the same color. So I need to decide where those end up. So if I highlight, I could have white and then white, and that's going to give me, oops, if I do this in the same color blue, 6 out of 15 times 5 out of 14 gives me 2 white socks. If I highlight it in red, I could also have 2 gray socks. Well, that's going to be 4 out of 15 times 3 out of 14. And the last one, highlighted in green here, I could also get 2 black socks, which would be 5 out of 15 times 4 out of 14. Okay? And I'm still using a very similar probability formulas to the one I was using before up at the top, that P of A times P of B equals P of the intersection between A and B. What I'm doing this time, though, is my probability, I'm multiplying P of A times P of A, or P of B given A, equals probability of A intersect B. Okay? And what I get here, then, if I multiply these all out, I'm going to get 30 over 210. I'll get 12 over 210 here, and I'll get 20 over 210. I then sum all my probabilities up. So 30 over 210 plus 12 over 210 plus 20 over 210. That's going to give me 62 out of 210, which I then simplify. If I divide both of those by 2, I'll get 31 over 105 as my final probability here. Or you can turn it into a decimal. 31 out of 105 is actually approximately 2.295. Okay. So there's a couple examples of using tree diagrams. They're really, really helpful when you have multiple events occurring after each other and you're trying to determine what's the probability you end up with so many heads or so many socks of certain colors, or we frequently see this with batteries and things like that. So if you have any questions, please feel free to ask in class. I'm more than happy to help. Otherwise, thank you for watching and have a great day, everyone.